Okay, so yesterday's probability question. I think this one was relatively easy because when I did it, I didn't even have to correct it a second time. It was just basically correction on top of my work, original work. So I think this one was relatively easy and it was like more of a book work than actual like let's say, it requires thought process. So let's look into the questions. In part A, part one, we have a probability space is a triple mathematical object of this. State what this P is and list the axioms that it satisfies. Okay, so this P is just the probability measure. This is just the definition. And there are three axioms which we should know. Is the first one is non-negativity, so the probability of any event is greater than or equal to zero. The second one is normalization, which basically means if we have like the entire space, then the probability would be one. And then for the third one, it's called countable additivity. Basically, the idea is that if we have disjoint events x1 all the way to xn, then the union of these events, their probability would equal the sum of their probabilities. Because since they have nothing in overlap because they're disjoint, then their probability would just be summed. There's no overlaps. That's the idea. And part one is done. In part two, we're asked to show that the axiom imply that for A, B, that are events, we have PA is smaller than or equal to P probability of B, whenever A is a subset of B. So over here, we're just going to assume that A is a subset of B. Then we can rewrite B as equal to B, not part of A, and then union of A. So this part in A partitions B because it could either, whenever we split a set, we can either have the case that we have something of A and then the rest of the things that are not in A are part of B, right? That's the idea. This part. And then we can just split it up by this part and this part. And then when we take the probability of this, probability of B is equal to the probability of this thing over here. And then by axiom 3, since A and B, not including A, are disjoint, so there's no kind of overlaps, then we can just write it as PA plus P of B, not including A. And then by axiom 2, we know that probability of anything has to be greater than or equal to 0. So the probability of A is smaller than the probability of A plus something, right? And this over here on the right-hand side is probability of B. So probability of A is less than or equal to probability of B. So we're done with our proof. So A was really just bookwork. Um, I'd say B, it's kind of similar to the collection question, except it's made much easier because they gave the standard density function right here. So recall that a standard normal distribution has density this thing, right? Let Z be a random variable with standard normal distribution. Compute the absolute value of Z, um, expected value of Z. So we have this is our density function z be the random variable with standard normal distribution. So we're trying to find this. This is essentially technically from negative infinity to infinity of the absolute value of z times density, right? dz. Yeah. Pretty straightforward, the definition of expectation. And we can take advantage of the fact that we know a normal distribution is symmetric because it's an even function. And that means, especially because we're here, it's standard, then it's around the mean is 0. So it's definitely symmetric around the axes. So basically what we can do is if this was the original distribution, like the bell-shaped curve, now if the absolute value of z, the density function would look something like this, just double the previous side of that. So it would just be double the density at each point, right? Pretty straightforward. So E of the Z would just be the sigma from Z to infinity of Z times 2 times of the density of Z, right? And then next what we do is just we substitute the sigma, like the density, right into here. And we get this. Then it's just a bit of algebraic simplification. We move the constants out of the integration. Then we see that, okay, this is just um, E of negative z squared divided by 2, and this is negative. We put in infinity. Infinity tends to 0, that thing, because it's negative, right? And the e of 0 is just 1, so it would just be this thing. And then when we simplify this would just be square root of 2 divided by pi. I technically got the same thing, but I think this form just looks nicer. Then moving on to part C. Part C is just looking for difference equations. I sort of messed up with the first one because I just didn't read that it was in. I didn't really think I just treated in as a constant, which was my mistake, but it's pretty standardized. How we approach like doing difference equations would just be first find the characteristic equation, then move on to finding the particular solution, then combining them and using the boundaries conditions to find what the final kind of equation is. So here we have this. So we kind of just do this, and this rearranging, we get to this form, right? So we're going to first start off with our characteristic equation, which is x minus 2 equals 0. So then we get our x is equal to 2. So then we know that the form would definitely be something to the 2 to the n. And then we have just a constant multiplied to that, right? And because we see here that the constant was not like an actual constant, but actually in. So we know that the form for the particular has to be in the form of ax plus b. So then we just put this in and we would get a times n plus 1 plus b minus 2 times an plus b equals n. And then we just rearrange this, and by this time we can just smash the coefficient, right? Both sides have to be the same. So then in here we have n is 1 over here. In order for that to be the case, n has to be equal to negative 1. And then because a is equal to negative 1, then b has to cancel a out, so b has to be negative 1. So our particular solution is negative n minus 1. So then over here, our u of n would just be the form of something a to the 2 of n minus 1. And then now we just plug in the boundary condition when u of 1, like u of something. What was the condition? When u of 0 is equal to 1, we plug this as the boundary condition and we find that a is equal to 2. When a is equal to 2, this is essentially, we can rewrite it as 2 to the n plus 1, right? And then we keep whatever we have. So that was that question. I'd say the thing that I really got wrong here was that this part n is not a constant number. It's not like 1, 2, or 3. It's n. So I kind of missed out and then didn't do a plus b. I rather did just c, which was not okay. But I think that was like the mistake. But for part 2 and part 3, it was all right. Like I was able to do it. Just it's the same idea. Just first characteristic, then particular, then finally combine it together and see what we have. This one doesn't even have the, what is it called? Particular solution because we see that it's equal to 0. So we just solve the characteristic equation, we get the thing, we just find what a and b are by the boundary conditions. Great, we got this. Combine it, and great, we're done. For part 3, the specific thing is that we have a double root. So for a double root, what we do is it's 2 to the n, and then the next one would be n times 2 to the n. And if there was a third one, it would be n squared times 2 to the n, so on and so forth, right? And then there's a particular solution which we just plug in and we find that it's equal to 1, so we just plus 1 over here. Then we use the classic boundary conditions to find what a and b are, and then we get to this form. And now one further step from this form to make it look nicer is just to combine the n minus 1 together and extract out the 2 to the n. So it looks slightly nicer, but essentially we get to the same solution. Okay, cool. This was pretty standard. I think this question was really easy. The only really thing that really caught me off guard was this part. But other than that, I think it's good. End it off here.